Hello everyone, thanks for watching the video today. And in this video, we're going to continue on with our study of polar coordinates. But now that we've recovered all of our polar coordinate knowledge that we learned in pre-calc, now it's time to bring on some calculus. Okay? So let's start with slopes and tangent lines. To find the slope of a tangent line to a polar graph, consider the differentiable function defined by r equals f of theta. So r is changing by some function f of theta. To find the slope in polar form, we use the parametric equations. X equals r cosine theta, which is now f of theta cosine theta. And y is r sine theta, which is now f of theta sine theta. Using the parametric form of dy dx, in the previous section we talked about parametrics, we now have dy dx equals dy d theta over dx d theta, which is simply two product rules, as you can see there. So to sum up, that is our, I guess you can call it, formula for derivative of polar form equations. With that, we can now do all the things we've been doing all year with rectangular and parametric equations. Find horizontal tangent lines, we set the numerator equal to 0. To find vertical tangent lines, we set the denominator equal to 0. And if they're both 0, then we cannot make any conclusions about vertical or horizontal tangent lines at those points. All right, let's take a look at a problem. Consider the cardioid described by the polar equation r equals 1 plus sine theta. Find the slope of the tangent line to the cardioid when theta equals pi over 3. All right, so first of all, parametrically, we can rewrite this as xy is going to be r cosine theta, r sine theta, right? That is the parametric form for that. And then in this case, we're going to do 1 plus sine theta cosine theta, comma, 1 plus sine theta sine theta, because that is replacing r with what r is, 1 plus sine theta. All right, so now here comes the calculus. So we know that dy dx is going to be dy d theta over dx d theta. All right, so now we have a choice. Do you want to take the derivative like this, the way it's currently written, or do you want to distribute the cosine and the sine? And honestly, it might be easier if we simplified this first. So let's see, that would be cosine plus sine cosine. Just bring this down here. Comma, sine plus sine squared. Either way, it's not going to be a pretty derivative to take here, but you can either do the derivative, sorry about that, you can either do a derivative like this with the product rule and this with the product rule, or this with the product rule here, but at least no product rule here. So this way might be a little bit easier to do the derivative. All right, here we go. So remember, this is going to be dy d theta over dx d theta. So dy d theta, the derivative of sine, is just cosine. And the derivative of sine squared is 2 sine cosine. All over dx d theta, so the derivative of this. Derivative of cosine is negative sine plus the derivative of sine cosine. We need a product rule for that, so that would be sine times negative sine plus cosine times cosine. All right. Now, if you want to clean this up a little bit, you can. The numerator, not really much we can do that unless you want to factor out a cosine, but I'm not going to bother with that. The denominator, we have negative sine theta minus sine squared theta plus cosine squared theta. Okay. Next, we want to find the slope at theta equals pi over 3, right? So that's next on the agenda here. that's going to be dy dx at theta equals pi over 3. Need our unit circle knowledge for this. So we have cosine of pi over 3. Cosine of pi over 3 is 1/2 plus 2 sine pi over 3, which is root 3 over 2, times cosine pi over 3, which is 1/2, all over negative sine pi over 3 minus sine pi over 3 squared, so root 3 over 2 squared, plus 1/2 squared. All right, so simplifying here, we get 1/2 plus, those 2's will cancel, 2 root 2 over 2, which is just root 3. It's actually root 3 over 2. Sorry about that. So root 3 over 2. And then we have negative root 3 over 2 minus 3/4 plus 1/4. All right, now really our goal is just to simplify that down as much as we can. So let's see, that would be 1 plus root 3 over 2 over negative 2 root 3 over 4. But, well, I guess I probably don't need to get a count down here. Yeah, let's not do that yet. So negative root 3 over 2. And then negative 3/4 plus 1/4 is negative 2/4, or just negative 1/2. So I can rewrite this as negative root 3 minus 1 over 2, which can simplify down to 1 plus root 3 over negative root 3 minus 1. And if I factor a negative out of the denominator, I'm left with 1 over negative 1, or just negative 1. So my slope there would be negative 1. Okay, part B says find the points in the cardioid where the tangent line is horizontal or vertical. All right, so let's go ahead and split this up here. All right, so we're going to do horizontal here, and we're going to do vertical over here. All right, so for horizontal, remember that means that the slope would be 0, which means the numerator would be 0. So cosine plus 2 sine cosine. I'm going to factor out a cosine. So it'd be cosine 1 plus 2 sine equals 0. So either cosine equals 0 or sine would equal negative 1/2. So this is going to happen at pi over 2, 3 pi over 2, and then sine would be negative 1/2 at 7 pi over 6, and 11 pi over 6. So we got 4 options for where theta would give us a horizontal asymptote. All right, so then what we're going to do with those 4 numbers is find the y values there. I guess you call them the y values, the outputs there. So r of pi over 2. Now remember, r was 1 plus sine theta, right? So let's just copy that down here. 1 plus sine theta. So r of pi over 2 is 1 plus sine of pi over 2. Sine of pi over 2 is 1, so 1 plus 1, which is 2. So my point would be 2 comma pi over 2. All right, we'll do that 3 more times here. So r of 3 pi over 2, 1 plus negative 1, which is 0. So it would be 0, 3 pi over 2. R of 7 pi over 6, 1 plus sine of 7 pi over 6 is negative 1/2. So 1/2. So 1/2 comma 7 pi over 6. And r of 11 pi over 6 would be 1 plus negative 1/2 as well. So then we have 1/2 comma 11 pi over 6. So those are the 4 possible points for horizontal asymptotes. I say possible because we still have to check for vertical as well. All right, so for vertical, we're going to set the denominator equal to 0. The denominator was negative sine minus sine squared plus cosine squared. So negative sine minus sine squared plus cosine squared. You might be thinking, you can't really solve that right now. And you're right, the way it's written, we're probably not going to be able to solve that. But luckily, we know our trig identities, and I can convert cosine into, remember, because sine squared plus cosine squared equals 1, so cosine squared would equal 1 minus sine squared. So now, I'm going to bring all this over to the right. I get 2 sine squared plus sine minus 1. So it'd be 2 sine and sine. And this would be 1 and 1. So this would be positive and negative. So sine theta equals 1/2, or sine theta equals negative 1. So theta is either going to be pi over 6 or 5 pi over 6 or 3 pi over 2. Okay, so now we're going to find r of those values. So r of pi over 6, r of 5 pi over 6, and r of 3 pi over 2. But in fact, I'm not going to even need to find the last one because we already did it over here. And because of what we said here, if both of those are 0, we can make no conclusion. So really, we can get rid of that and get rid of that. So r of pi over 6 would be 1 plus sine of pi over 6. 1 plus, and the sine of pi over 6 is 1/2, so it's 3/2. So my point is 3/2 comma pi over 6. 1 plus 1/2 again, so 3/2. So 3/2 comma 5 pi over 6. And that's our 2 vertical tangent lines. So this graph would have 3 horizontal tangent lines at these points here and 2 vertical tangent lines at these points here. We can't make any conclusion about 3 pi over 2. All right, last one. Particle motion of a polar curve. A polar curve, and we're going to need our calculator for this as well. A polar curve, r is given by r equals theta plus cosine theta, where r theta is between 0 and 2 pi. A particle is traveling along a polar curve, r, so its position at time t is x comma y, and such that d theta dt equals 1/2. This kind of sounds like it could be some type of related rates problem. Find dx dt at the instant theta equals 5 pi over 6, and interpret the meaning of the answer in context of the problem. Okay, so since we're looking at trying to find dx dt, we should probably start by knowing what x is. And x, remember, in parametric form here is r cosine theta. So for this problem, it's theta plus cosine theta, cosine theta. All right, you can leave it like that, or you want to do theta cosine theta plus cosine squared theta. That's fine too. It really doesn't matter. Either way, we got to next find dx dt. So now we have to take our derivative, dx dt, and again, you can use whichever one you want here. I'm going to use the second one. So that's going to be product rule, theta times negative sine theta d theta dt plus cosine theta times d theta dt plus 2 cosine theta times negative sine theta times d theta dt. All right, so then dx dt when theta equals 5 pi over 6. So we have 5 pi over 6. The sine of 5 pi over 6 would be 1/2, so it's negative 1/2. D theta dt equals 1/2. Plus the cosine of theta would be negative root 3 over 2. times d theta dt, which would be 1/2, plus 2 cosine of theta, which is negative root 3 over 2. Negative sine theta is negative 1/2. d theta dt equals 1/2. All right, so that gives us negative 5 pi over 24 minus root 3 over 4. And this last part here would be negative positive root 3 over 4. Simplifying that, negative 5 pi over 24. I guess we don't need a calculator for that. Negative 5 pi over 24 is our answer. Okay, so it does say to interpret our answer in the context of the problem. So that would simply, since it is dx dt, this represents the horizontal rate of change of the particle as it's traveling along the curve, the polar curve, when theta equals 5 pi over 6. Okay, so I'll say that again for you. dx dt represents the horizontal rate of change of the particle as it's traveling along the polar curve at the instant theta equals 5 pi over 6. All right, that'll do it for today's lesson. Thanks as always for watching, and we'll see you again soon.